Good evening. Welcome to my final project presentation. First, we'll walk through the crop choices, then move on to the water balance, and then the energy balance, and finally, the PFD. To start out, I made a table with the provided information about the astronauts, then calculated the energy requirements through these equations with the given data, broke it down to the percentages of macronutrients and calculated the totals grams per day using these conversions. Once I did that, I wrote down relevant information about the crops from tables 4-97 and 4-98 and set up some equations that took these variables and the amount that was to be produced as inputs and outputted data in the macronutrients grams, the area used, the water uptake, and the oxygen. Based off of those variables and the mental health of the astronauts, I chose a variety of different crops. As you can see here, they satisfy the required macronutrients in grams per day levels. Once I knew exactly what crops I was producing and how much, I calculated the water uptake and supplied 10 times that amount. The water that was taken by the plants was assumed to be fully leaving the system in one of two ways, either through the edible or inedible portions in the water content of the crop. The water content in the edible portions was eaten by the astronauts and then removed from the system as human solid waste. The water in the inedible portions of the crop was discarded as unusable crops. The second part of the water balance was the amount of water that the crew members would be drinking, and that was the same for everyone. 13.5 kg of that was being recycled every day, and the rest was leaving the system. These columns here show the consolidated data for the water balance. Once I knew how much water the irrigation systems were using, I could do the energy balance. The first three statistics, the farm lights, the air filtration, and the heating, were pretty straightforward to calculate. For the farm lights, I just had the area as an input because I knew what crops were reproducing, and then I converted them all to kilowatt hours per day. For the heating of the water, first I found the mass, and then I split up the heating into the phases from -40 to 0, the phase change, and from 0 to 20. Then I used the relevant equations, as you can see, the MC delta T and the M times the delta H of fusion equation. For the pumping of the water, I found the mass, and then converted the 1,000 gallon statistic into kg per day, and used that to calculate the amount of energy to pump the water. And for the water filtration, I did something similar, converting the volumes to gallons. Total required energy was in kilowatt hours per day, 36,435. In order to supply this energy, it was decided that we were using a nuclear generator, simply because it would take too many solar panels to power this. Even with NASA's 34% efficient panels, it would take around 80,000 square meters of solar panel area to power this station. Also, the dangers from a nuclear power plant would be severely mitigated on Mars because A, it's an uninhabited planet, so the power plant can be set up very far away from the base, and additionally, the atmosphere on Mars is primarily carbon dioxide. This is the process flow diagram that I generated. As you can see, the top half is the water balance for the drinking water, and the bottom half is for the irrigation system. Thank you.